This is a quick video about covalent bonds. I'm following chemistry, the central science. This is chapter 8, third section. My previous video was on ionic bonds, which is one type of bond. It's a type of bond that especially involves the sides of the periodic table, a metal with a nonmetal. Covalent bonds tend to be between nonmetals and nonmetals. And basically, unlike an ionic bond, so an ionic bond holds together because of the charge between them, and it tends to be a complete transfer of electrons. So sodium gives its electron away and chlorine takes its electron. That's ionic bonding. Covalent bonds have to do with bonds that are formed by sharing electrons. So it's not that one of the atoms gives up its electron and the other one takes it in the way of sodium and chlorine, but rather both atoms share the electron in common. So it gets to the octet rule still applies, and it gets to 8 in many cases, but it gets to 8 by sharing rather than trading, as it were. Ionic bonds trade electrons, covalent bonds share electrons. So how does this work? Well, for quantum mechanical reasons, that is the math of the atomic world, as it were, the physics of the atomic world, electron density, so electrons aren't really located in a spot. Rather, what we have is kind of a probability cloud, a probability that an electron could be at any one particular point. And so if you look at this very badly drawn hydrogen molecule, H2 molecule, so you have here hydrogen, hydrogen. So here's the nucleus, the positively charged nucleus. And what you have around these two nuclei is a probability distribution. So it's not that these are not electrons. I mean, it's hydrogen, right? There are only 2 electrons involved. And so what this cloud is, it's not a cloud of electrons, it's a probability cloud of 2 electrons. And what we find is that when you do the quantum mechanical math, there is a higher probability that these electrons will be located here between the 2 hydrogen nuclei than, say, out here. So yes, I mean, frankly, the electron could be millions of light years away, but the probability, so this is not a hard and fast boundary, but the probability of where the electron is that there's less probability that these electrons will be out here than there is that these electrons will be in here. And so there is an attraction that the nuclei, that is, the nuclei of hydrogen, are attracted to the concentration of electrostatic charge that is concentrated here in the middle. And so it's a probability attraction. Because the electron is more likely to be here, the charge is more likely to be here, and the positive nuclei are attracted to that concentration of negative electrostatic charge. So that's how covalent attraction works. Okay, Lewis structures. So basically these are 2 different ways to express a chlorine Cl2 molecule. So you'll notice now if I were to take one of these apart from the other, we would only have 7 electrons around the chlorine. So the neutral state of chlorine is to have 7, and so 1, 2, 3, 4, 5, 6, 7. So where does this 8th one come from? It comes from the other chlorine. By putting them together, 7 plus 7 equals 16. Not really, but you see what I'm saying? By taking the 7 of this chlorine and putting here, the 2 chlorines can share their 7th molecule, their 7th electron, as it were, and thus get to 8. So now I have 8 around both of them because they're sharing these 2 in common. That's a single bond, so we can draw it like this. So here are the 6 electrons that are happy because they're paired up. And then the 7th electron is shared between each one, getting to a total of 8. So this is the way to typically write a single bond between, say, 2 chlorines. You can also have double and triple bonds. So there's the single bond of 2 hydrogens, but you could also have double bonds marked by 2. So like in carbon dioxide here, CO2, you have 2 bonds, which is basically the carbon, all four of its electrons, or its four electrons are being shared with the oxygen to get to 8. So we have 8 around everything because they're sharing in that double bond. You could also have a triple bond, which is, of course, a stronger bond. And the distance between bonds, the bond length, not surprisingly, decreases as the number of shared electron increases. So the distance between these two nitrogen nuclei is going to be smaller, a smaller number of angstroms than this, where you only have one bond. And this is going to be, a double bond is going to be somewhere in the middle. Okay, so there you have a little bit on covalent bonds. More to come.